Okay, let's finish up this determinant of square matrices stuff. We left off just about to look at properties of the determinant. So here's our dilemma. Calculating determinants is just tedious unless we got a bunch of zeros. So what are you going to do if you ain't got a bunch of zeros? We could use row reduction to introduce zeros, but row reduction may change the value of the determinant. If it doesn't, fine, have a ball, but it does. The properties of determinants, as stated in theorem 4.2.a, are as follows. So this is going to tell us, in particular, how elementary row operations change determinants. And the good news is they do change it sometimes, but they don't change it a whole lot. Property 1. The determinant of A is the same as the determinant of A transpose. Possibly not terribly surprising, you interchange the rows and the columns when you go from A to A transpose, and we know we can expand determinants along either a row or a column by the theorem we saw previously, so that shouldn't come as a big shock to you. Knock yourself out. The proofs are in the supplemental notes, and they're based on induction. But let's just take all this as given. Row interchange property. So this is one of the elementary row operations. Transpose is not, but this is. If two different rows of a square matrix A are interchanged, the determinant of the resulting matrix is negative determinant of A. Equal rows property. If two rows of a square matrix are equal, then the determinant of A equals 0. Geez, that's going to follow. I'll leave it to you to read the proofs, but that'll follow from this previous one. So interchange two rows, change the determinant by a negative. Two rows are the same, determinant's 0. We've seen when two rows are the same in a matrix, we've seen that lead to some stuff in the past. One of the things it might have led to would be linear dependence. Another was free variables in a consistent system of equations. The scalar multiplication property, another elementary row operation. If a single row of a square matrix A is multiplied by a scalar R, the determinant of the resulting matrix is R times the determinant of A. So let's see, row interchange swaps determinants by a negative sign. Scalar multiplication of a row modifies the determinant by a scalar multiple of R. See, if we avoided those, that might be to our advantage. The really good news is property 5. The row addition property, so what are the elementary row operations? Interchange rows, multiply row by non-zero constant, and row addition. If the product of one row of A by a scalar R is added to a different row of A, the determinant of the resulting matrix is the same as, there's my favorite one, same as the determinant of A. So I add 3 times the first row to the fourth row, doesn't change the determinant. Who's your favorite, most productive row operation? Well, it's probably this one, row addition, because this is the one where you introduce zeros. We'd take an entry and we'd target it and we'd make it 0 through some sort of row addition. The multiplying by scalars, well, unless we're trying to get the thing in reduced row echelon form, we don't really need to multiply a row by scalars. Row interchange, geez, the row interchange we're probably going to be stuck with. But to perform changes of a matrix that produce a new matrix for which the determinant's easy to find and the determinant's not too different from the original matrix, we're going to use row interchange, because we'll have to, and we're going to use this row addition property. We're going to avoid using scalar multiplication and the other stuff. Maybe property 3 is useful as a shortcut to notice when determinants are 0. But the plan's going to be row interchange and row addition Try to avoid the scalar multiplication, multiplying a row by a scalar. And the only changes that'll have in the determinant as we go through the computations is introducing a multiple of a negative every time we interchange two rows. So that's what this note 4.2.a basically says. So the plan is, let's introduce zeros as much as we can and do that using the row addition stuff. Maybe we can swap around some rows as well. And by swapping around, we might be able to put a matrix in row echelon form. Probably not reduced row echelon form, in which the case the pivots are 1. How'd you get those pivots to be 1? Well, if they weren't 1, you divided them by whatever they were to create a 1 for a pivot. And we're trying to avoid dividing rows by scalars. So what we're going to do is try to take matrix A and reduce it down to an upper triangular matrix. We're going to put it in row echelon form without multiplying rows by scalars. So we're going to do the row addition stuff and we're going to do the row swapping stuff. Get it in row echelon form, and if that row echelon form is as it should be, if it's upper triangular, well, we were just talking about how to find the determinant of an upper triangular matrix. So let's look at an example and take advantage of these new properties. Okay, so use row reduction and then find the determinant of this matrix. Okay, 4x4 matrix. It's got a handful of zeros in it. I guess my favorite column is column 3 because it's got 2 zeros in it. But I think we can do better than that if you turn me loose with row reduction. So let's do our row reduction deal. We'll take the 2 and use it to eliminate the entries below it. Nice pretty numbers, so we don't encounter any fractions in any of this stuff. We'll do the row operations. Trust me on the arithmetic here. Some ugly numbers on the right, but lots of zeros on the left. Next, let's use the 1 to eliminate the stuff below it. Okay, let's see. Now I need to do something with this. I like the first column. I like the second column. I didn't put that 0 above the pivot. That 0 was given to us above the pivot. So we're not going necessarily for reduced row echelon form. I'm getting zeros below the pivots. Also, hey, these are just row addition operations. These don't change the determinant. So the determinant of this matrix is the same as the determinant of the original matrix. And this one's got a bunch of zeros in it. So I like this one better. But determinants are the same. We know that by the previous theorem because all we've done is row addition. Let's do more. I could use this 11 to eliminate that -1. That introduced some pretty ugly numbers. So I tell you what, let's swap row 3 and row 4. Swap these two rows. Oh, that's going to change the determinant though, but it's going to change it by a negative sign. So keep a tally somewhere. That's 1 row interchange. So that means introducing a multiple of -1. So let's swap those rows to produce this. Now let's use the -1 to eliminate the 11, and then we'll avoid some fractions. So we'll use, here it is reproduced here, we'll use the -1 to eliminate the 11 in the usual way, and that'll produce this matrix here. Let's call it matrix A. How is matrix A related to the original matrix A? Why, they are row equivalent, and with this stuff, we got to keep track to a degree of what the row operations were. We had a bunch of row additions. I guess we had 6 row additions, and we had 1 row interchange. Well, good news, all those row additions, and that's what introduced the zeros. They don't change the determinant. The 1 row interchange, that does change the determinant, but you know how it changes the determinant. It changes it by a negative sign. So what's the relationship between A and H? They are row equivalent. What's the relationship between their determinants? The determinant of H is 1 -1 multiple of the determinant of A. Determinant of A equals negative determinant of H. Why? Because of that one row interchange that we did in producing H. Also, excellent. This is an upper triangular matrix. Below the diagonal, only zeros. Above the diagonal, nobody cares. We've got zeros below the diagonal. Well, I could keep hacking away at it and put it in reduced row echelon form, but I see some ugly numbers coming. I'd have to do some scaling along the diagonal to make all those pivots one. We can find the determinant from the information here, so leave it alone at this stage. So the plan's going to be put these matrices in row echelon form, not reduced row echelon form, and do it by using row addition and row interchange only, because you can. It can be put into an upper triangular form using only those row operations. Hey, we just said we got an upper triangular matrix. I could do this slow motion and expand along the first column and then expand the result along the first column and so forth. But we already know all we have to do is take the product of the diagonal entries in an upper triangular matrix. So the determinant of matrix A would be 2 times 1 times -1 times -7. I'm sorry, the determinant of matrix H would be the product of these entries here. Determinant of H is the product of those entries. That produces 14. So the determinant of the original matrix A, we know to be the negative of that. So the determinant of matrix A is -14. You look back at this original matrix, and this was a healthy step forward. Hey, that matrix, 4 by 4, I'd have to take 4 determinants of 3 by 3s. At least I could take advantage of some of the zeros. This is way easier because you're good at row reduction. You introduce a bunch of zeros, preferably creating upper triangular matrix, and you're good to go. Then I can easily calculate the determinant of this, keep track of those row operations that got you here, and then I can relate the determinant of this matrix to the determinant of the original matrix. And that's the only way to fly. Back to the notes. We have a load of conditions for a matrix to be invertible. Square matrix is invertible if and only if the columns are linearly independent, the rank is in for an n by n matrix, the nullity is 0 for an n by n matrix. Of course, invertibility, much like determinants, only makes sense for square matrices. And there were a handful of others, something about unique solutions to consistent systems of equations, a unique solution to a homogeneous system of equations. Here's another one to add to the list, and I think I want to skip the proof of this. It says, matrix A is invertible if and only if the determinant of A is non-zero. We called non-invertible matrices singular. Think singularity is a bad thing. You take differential equations, you'll run across singularities of a differential equation. The center of a black hole is called a singularity. The reason it is for some differential equations reasons, in fact. But singular is bad. So a matrix is not invertible, it's singular, if and only if the determinant equals 0. Determinant equals 0 is bad. Determinant non-zero is good, in the sense that non-zero determinant, invertible matrix. Zero determinant, non-invertible matrix. A very useful property of determinants is the following. I also want to skip the proof of this. It says, suppose A and B are both square matrices, then the determinant of the product is the product of the determinants. Now that's totally unintuitive because determinants are computed in such an oddball way in terms of these minor matrices and all that expansion stuff. Proof's in the supplemental note, so help yourself. But determinant of a product of matrices is the product of the determinants. So let's gloss over those couple of proofs and just look at a bunch of examples. So to the supplemental notes, multiplicative property. Whoops. Let's see here. Okay. Number 28 from the book says, this is an odd question, but it foreshadows what's next. Find the values of lambda for which the matrix A, is given here, is singular. Okay, that's related to determinants in terms of the determinant being 0. So we could reword this question as, find the values of lambda that make the determinant of matrix A 0. Theorem 4.3 said, singular matrix, non-invertible matrix, if and only if the determinant's 0. You haven't seen the last of this kind of question. In the next section, when we address eigenvalues, or maybe it's the next chapter, when we address eigenvalues, we'll be doing lots of computations like this. Okay, so here's a 3x3 matrix. We'll take its determinant, set it equal to 0. That'll give us an equation involving this lambda that we're looking for. All right, determinant of a 3x3 matrix. I'd say expand along the first row or the first column. It doesn't matter, we get the same computations either way. We'll have 2 minus lambda times the determinant of the minor matrix. Say if we go along the first row, minus 0 times something plus 0 times something. I don't care what the somethings are. They're determinants of 2x2 matrices, but it doesn't affect the numbers, so we don't need them. Okay, that'll give us 2 minus lambda times the determinant of this 2x2 matrix. 1 minus lambda times 1 minus lambda, minus 4 times 1. Multiply out, do your FOIL thing and collect together terms. We'll get, we'll get lambda squared minus 2 lambda minus 3 upon multiplying out and simplifying. Can you factor this? Remember, we want this determinant to be 0. We're looking for lambdas that make the determinant 0. So factoring is the way to go. Lambda squared minus 2 lambda minus 3. Yeah, that factors is lambda minus 3 times lambda plus 1. Lambda minus 3 times lambda plus 1. Don't distribute. Right, you want to multiply all this stuff out? No, you want to find where this stuff is 0, and you do that by factoring. So don't waste your time multiplying out when the ultimate goal is to factor. You multiply out now, you're just going to have to undo it later, given the nature of this question. So we've got the determinant of A written as this product in terms of the unknown lambda. We want the determinant of A to be 0 because we want matrix A to be singular, that is to be non-invertible. Well, then we need the lambda, the expressions here, to be 0. That is lambda to be -1 from this expression, lambda to be 2 from this expression, or lambda to be 3 from this expression. So the lambda values are -1, 2, and 3 that make this 0. Little foreshadowing here. I've listed the lambda values in increasing order. -1 first, then 2, then 3, because that's how they lie along the real line. We'll be doing lots of this, and I want to set up a consistent pattern. And it doesn't matter what order you list them in, but I got my reasons for listing them in this order. So we've got that the determinant of A is 0 and A is singular if lambda takes on any of these values here. And yeah, you're going to see a lot of this in the future, in the next chapter. So let's do another one. Okay, this is a little argument involving inverse matrices. Well, it's sort of proofy. Well, it's not horrendous, so let's go through it. So suppose matrices A and B are n by n square matrices. If A is singular, so A is non-invertible, the determinant of A is 0, as we just saw. Prove, without using theorem 4.4, that the determinant of AB is also singular. Theorem 4.4 is the one that said the determinant of the product is the product of the determinants. And granted, this would be easy enough. Showing singular is like showing determinant is 0. Well, they're not going to let us use that, so we're going to have to try something else. Okay. Let's go for a proof by contradiction. Suppose A is singular, that is A is not invertible, and suppose the conclusion is false. Suppose that AB is not singular, non-singular. Singular means not invertible, so non-singular means is invertible. So sorry about the logical gymnastics, but Suppose the thing is false. Suppose A is singular and AB is not. What does it mean to be not singular? It means to be invertible. So the matrix product AB inverse exists. So there is some inverse of that matrix because it's non-singular. That matrix AB is invertible, as we've assumed. This is going to cause some problems. That's how we get a contradiction and finish the proof. So this is an alleged inverse of matrix AB. So if we take matrix AB and multiply it by this alleged inverse AB inverse, we'll get the identity matrix. All right, let's do a little associativity here from way back when in chapter 1. We can take the product of B with the AB inverse first, bracket those two together, and then multiply by A. It's just associativity. So now we've got a matrix, this one here, B, AB inverse, that when we multiply by A on the right by, we get the identity. But that means this matrix is an inverse of matrix A. At least it's what might be called a right inverse. When you're dealing with square matrices, left inverses and right inverses are the same. For the record, that was theorem 1.11. It's sufficient with square matrices to establish a one-sided inverse. That's what theorem 111 really implied. But we can use associativity to draw this conclusion here. Hey, that means B, AB inverse is an inverse of matrix A. But we started with a hypothesis that A is singular. A doesn't have an inverse. A is not invertible. Well, that's a contradiction. So we assumed something. We assumed AB was invertible, non-singular, and we drew the conclusion that A is singular. We drew a conclusion of a contradiction. Well, whose fault is that? The unfounded assumption we made. So the assumption we made that AB is non-singular must be false. AB is in fact singular. That is, AB itself is not invertible, and there doesn't exist such an AB inverse. If there did, we got a problem in this setting. That is, AB must be singular. That was the claim of the theorem, and there's your proof by contradiction. You assume the negation of the claim, get a contradiction. That assumption must have been false. Let's do another one. Okay, this one is quite useful. It's kind of written up as a proof, but it's really computational. And this time you can use the multiplicative property of determinants. The only reason we couldn't in the previous one is they told us we couldn't. That one we could have worked with the multiplicative property of determinants as well. But the claim is, suppose A and C are square matrices with C invertible. Prove that the determinant of A is the determinant of C inverse times AC. We assume C was invertible, so C inverse exists. And they're giving us as a hint one of the previous exercises, actually it's that follows also from the multiplicative property, that if C is invertible, then the determinant of C inverse is 1 over the determinant of C. So finding determinants of invertible matrices is easy in terms of the determinant of the original matrix. Now, what you got here is C times C inverse equals the identity matrix. I mean, that's what an inverse is. Anyone? What's the determinant of the identity matrix? Well, it's got ones down the diagonal and zeros everywhere else. Dude, it's upper triangular. So its determinant would be the product of the diagonal entries. For an identity matrix, those are all ones. It'd be 1 times 1 times 1 n times. The determinant of the identity matrix is 1. In a sense, that's where that 1 right there comes from. Maybe we can, when we get time, cover exercise 31. Not terribly big on a lot of this proofy stuff in a class at this level. A little bit of it's necessary because this is a math class. But exercise 31 would be a good one to cover. I like it. All right. So assuming the statement in exercise 31 that the determinant of C inverse is 1 over the determinant of C, let's show these determinants are the same. Piece of cake, if we can use the multiplicative property. What's the determinant of C inverse AC? Well, the determinant of a product is the product of the determinants. So we can expand that out, done it using associativity and one at a time, as the determinant of C inverse times the determinant of A times the determinant of C. This is distribution, isn't it? No, because we're not multiplying, we're performing an operation called taking the determinant. It looks like some sort of distributive property. It's called the multiplicative property. It's theorem 4.4 that tells you the determinant of the product is the product of the determinants. It's not distribution. You want to think of it like that, just don't tell me about it. It's a good way to remember it, maybe. Okay, what do you know about the determinant of C inverse? Well, exercise 31 tells us it's 1 over the determinant of C. Okay. So let's take that information. Let's replace determinant C inverse with 1 over the determinant of C. Now we've got the determinant of C inverse AC equals this. Hey, wait a second. We're dividing by the determinant of C. We're multiplying by the determinant of C. The determinant of C is not 0, is it? No, we said C is invertible. So it's determinant non-zero from the theorem stated previously. So we can cancel those things. We're left with the determinant of A. And there's your claim. Determinant of C inverse AC equals the determinant of A. Now, why on God's green earth anybody would be interested in looking at C inverse AC, where C is an invertible matrix? Totally uninspired at this stage. But later on, we'll see this pop up a bit. Probably the class will end before we see a lot of it. The relationship here is one of similarity. When you have a matrix of this type here, we may bump into that word before we're done, probably not. But we've got our reasons to want to introduce these matrices C and consider these types of things for a matrix. For now, don't worry your pretty little head about it. It's just a computational illustration of the multiplicative property. And I think that takes care of this section. So have a nice day.